Okay, so here's the example. I would like to ask you the question: which face is real? Can you distinguish between the two faces in the slide? Do you think which one is real and which one is fake? Okay. If you go to the website wikifactsisreal.com, and you can see a lot of examples like this, and they challenge you to distinguish if one image is about a real face of a real human or not, right? So I could tell you that both of the images are not real. They are from uh, artificially generated image, right? So this is what to say that nowadays we can have the learning model that can generate quite, natural face of anybody or of somebody that have never existed, right? And from our point of view, we cannot, and it is really hard for the human layers to distinguish which one is real and which one is not, right? Okay, it's quite surprising and quite shock for most of the people, right? Okay, another example like this one is a deepfake, right? If you look into the internet and you search for some recent news, and you see that the deepfake, the video generated by the computer, nowadays they can swap the human, somebody into the movie, right? Like you have James Bond into the some Vietnamese movie, right? And it's look like real human, real Bond actor acting in that movie, right? Okay, or you can see the movie of Barack Obama saying something unnormal, right? Because it was generated by the computer, right? Okay. Okay, so here is that a summarization of two approaches in learning. This is not the only two approach, but we want to distinguish between supervised and unsupervised learning. We have another type of learning, which is reinforcement learning, but that topic is something out of the scope for this course, right? Okay, so here we focus on the comparison between supervised and unsupervised learning. In supervised learning, we have the data sample consist of two parts, the X and the Y. The X are the input feature, and the Y here is like the label, right? For example, X could be the image and Y could be the name of the person, right? So in supervised setting, the objective is to learn um, the mapping function from X to Y. For this specific X, which is the corresponding Y, right? For this specific feature, which is a class for this X, right? And the type of application could be classification problem, regression problem, object recognition, semantic segmentation, and machine translation. I can say that most of the tasks you are doing now with the machine learning model belong to the belong to the supervised learning task, right? Um, we have other tasks of other type learning, which is unsupervised learning. And in this unsupervised learning, the data sample consists of that uh, feature, and we have no associate label for the feature, right? So the objective of unsupervised learning is not about learning the mapping function because we have no label at all. So the objective here is to learn the hidden structure or the relationship from the input, right? For example, performing clustering, uh, I mean, uh, inferring the association rule, doing dimension reduction. These are the example of unsupervised learning algorithm, right? So for clustering, for example, we don't know which which sample belong to which cluster, right? For association rule, we don't know the rule before, right? For the dimension reduction, we don't know. I mean, which is a label, which is a dimension we want to map the input, the initial input dimension to that target dimension. We can say that, okay, for clustering, we want to find out, I mean, a number of cluster, but not specify which is the cluster, right? Okay. Okay, so I hope it is clear about the supervised and unsupervised learning. Okay. So now we discussed about generative. So generative model is one type of, unsupervised learning model where we have the neural network with many hidden layers. Okay, so here specifically we are discussing about the deep generative model, right? So the model, generative model that modeled by the neural network, right? We have other type of generative model, but they are not using the neural network as a backbone. Okay, right? So for deep generative model, they are the neural network with many hidden layers trained to approximate the distribution of the sample, right? Like to infer the hidden structure of the sample, right? And here to be correctly, we are having the neural network that try to approximate the distribution of the input sample, right? And the distribution might be complicated and might be in high dimensional, right? For example, if the input sample as the image, then you see the size of the image could be the width and the height, the number of channel in the image, right? Okay, so you see, I mean, to infer the initial distribution of this sample, it could be using the deep generative model, right? So the idea here is to the distribution of the sample, and from that we can generate, I mean, the similar input, right? So for example, here as the input image, right? And here is the image that can be generated by using the deep generative model that was trained to approximate the input distribution, right? If we train the model good enough, for example, in this example, we can see that the generated sample look for the human layers very, very similar to the input sample, right? And if we come back to our initial example here, you can see we already have the model that can generate the human face, look really natural as real human being, right? So it's quite surprising and for everybody, right? Okay. Okay, so to sum up, the idea of generative model is to learn the distribution of the input sample so that the generated, sample had the distribution similar to the input, so the distribution of the input sample, which is the the probability here, x here should be the same, and maybe approximate to the initial p here. Okay, so we want p model is approximate of p data, right? Okay, so so the generative model, learn the distribution of the input sample so that it can uncover underlying hidden information in the data, right? For example, it can generate more diverse and balanced data after you learned, after you train the generative model, you can use that model to generate more data, and you can control the generation of the new data, such as the data could be more diverse and more balanced, right? Okay, so here's another application of generative model, right? The first application is to uncover underlying hidden information in the data. For example, you can use a model here to for example, generate all of the face with the glasses, right? On the face with the smiling mouse, okay? Or whatever you want to generate, right? Another application of generative model. You can use this for outlier detection, right? The question is how to detect a rare occurrence of a new event, right? So the idea could be you can use the generative model to learn the distribution of the data, so that you can model the distribution of the data, and if some specific moment in time where you receive the input which is out of the learned distribution, then you can say that, okay, that was a anomaly, that was a normal event, right? For example, you have the self-driving car that train on, normal weather condition here, right? And then you can train the generative model to approximate this, environment, right? And at some point when you when the car observe this, rare occurrence where some plane across the street, for example. So you see the distribution of this image is really different from the distribution of the input training sample. So it can detect that, okay, this is animal, right? Or this is animal, and this is animal where you have the pedestrians cross the street, right? Okay. Okay, so I just have a quick introduction to generative model, right? I can say you again that there are a lot of different types of generative model, right? But here we are discuss the deep generative model, where the underlying network, the underlying backbone is neural network, right? Okay, so any question? Okay, so we can move to the second part of today. Here we discuss one type, generative model, which is autoencoder. So autoencoder is one type generative model. More specifically, is one type deep generative model, right? And this is an unsupervised learning model that allows to learn the feature representation with a smaller number of dimensions from the unlabeled training set, right? So this is to say that, okay, the model, the network can encode the input image into smaller hidden number of dimension. That's here, right? And this is considered as the learned feature representation in the smaller dimension of the initial input, right? So for example, from here to here is the network that let's say its name is encoder, and this encoder learn the mapping from the data X into the hidden space Z of lower dimension, right? We already have some discussion on what to vec, and what to vec also is one type of encoder that mapping the input text word into a fixed number of dimension vector, right? Okay, so question is, why do we care about a low dimension Z, right? We care about the lower dimension Z because we can use this Z for all the, down for all the tasks. For such as for doing image classification and for generate a new sample, right? As the application we are discussing here, right? Or we can use that for doing anomaly detection, right? Okay. So in the autoencoder model, right? In order to learn this small dimension representation of the data, we need to have two parts of the network. Okay, so the encode here learn to map the data X into hidden space of lower dimension, right? And the decoder, the second part of the autoencoder network, map the hidden feature Z back to recover the input data information, right? So this is specifically the architecture of autoencoder network. It have two parts, and the decoder, right? The encoder, convert or transform the initial input into, low-level representation text, and then the decoder decode that hidden feature back to reconstruct the input data, right? For example, if we have this input data, here is our one image of a digit, number 2, for example, here, and we want the autoencoder after the encoding from X to Z, and we want to decode Z to X hat, so that we want the output here is similar to the input sample, right? If we have the network doing like this, then we can say that here is the hidden feature learned by the model, and it can encode the information from the input, right? So you see, this is somehow relate to the sequence to sequence model we discussed lastly for neural machine translation, right? But for the sequence to sequence model, we have the first encoder that encodes the input sentence into a latent space, and then we have the decoder that decodes the latent space into the sentence in the target language, right? So in that translation, the input and the output are the sentence in different languages, but for this autoencoder network, so the objective of this network is to generate the same input, and the output which is similar to the input, right? But the idea is to first encode the entire input into a smaller latent space, and then from that we decode, right? Okay, so the autoencoder like the one we are discussing here doesn't require labor to train the network, right? Because if we can see that again, we want the output of the network to be the input. So actually, for every input we know, this is a target we want to approximate, right? Right. So the objective function could be any, distant function, say that minimize the distance from the X and the output of the network, right? Okay. Okay. So for the network, we know the objective function. We have the data, so we can use any type, neural network training algorithm to actually optimize the network so that we can find out the network parameter, the weight of every connection in the network, right? And after we minimize the loss, and we can use the network to find out the depth, right? The latent space of latent representation of every input, right? Okay, so here is the example about the result of training autoencoder, right? So for example, if we have the latent space of 2 dimension, right? Then you see the generated output is a little bit blurry. But if we increase the latent space to be 5 dimension, then you see the generated output are somehow similar to the very close to the Gaussian, right? Okay, so we can say that the autoencoder is one type of data compression, and if we have the smaller the number of hidden dimension, we choose the larger the training bottleneck, right? But if we choose a very large latent space, then maybe it doesn't. So if we choose a very large number of hidden dimension, then maybe the work we are doing here have very less meaning, because the idea is to encode the input image into smaller hidden dimension, right? So we have, with the purpose, we want to encode that into smaller dimension, right? But the idea is not doing that to be too small, so that it cannot reconstruct the initial input. Okay. Okay, here's some more discussion about the autoencoder network architecture. So the encoder, the hidden layer in the encoder as a bottleneck that force the network to compress the data representation, right? We want that at some point at the end of the encoder, the output of that layer are in smaller dimension, right? Okay, and then the decoder part, the objective function for the reconstruction, right? Because in that network we want the output of the network to be similar to the input, so we have the reconstructive objective function, and this objective function forces the hidden representation to encode as much information from the input as possible, right? So that's the reason why we say the network, that the model, the network is autoencoder, automatically encoding the data, right? Okay. Do I have any question? Okay, then I think that we can take a break for 5 minutes. Then we will continue. Okay, so let's continue. Okay, now we discuss about variational autoencoder, right? First, let's review a little bit about the autoencoder architecture. In this autoencoder architecture, every dimension in the encoding vector, each dimension in the encoding vector contains a single value that represents a hidden attribute from the input data, right? If you say that, okay, the that have a 128 dimension, then each element in that vector represents something, attribute from the input data, right? So if we choose the dimension of that is 128, then we say that the input, if the input image have 128 attribute, and the encoder and the autoencoder can only learn 128 attributes from every or from any input image, right? So for example, here we have the example. We have the input image of the face, and if we decided to encode this into, a vector of, of 6 elements like this one, then we, for the first element is to encode the smile, and the second to encode the skin tone, the gender, the beard, the glasses, the hair color, right? This is just the example saying that one element in the vector that represent one attribute of the input image, right? So of course, the first element in the vector here maybe it's not represent the smile, it's not represent render, but this is just the example saying, for example, if the first element to be about the smile, the second to be about the skin tone, the third to be about gender, right? Okay, so this is a latent space, latent vector of this input phase, and from that latent vector, the decoder will decode and try to generate the output, and the output, is expected to be close, to be similar to the input, right? Of course, in our example here, if we have the latent space consist of that 6 element like this one, for sure that we cannot generate the output as similar to the input phase here, right? Except that if we train the model for the phase of this only one, human, right? Okay, so that was a problem with the autoencoder, right? We have the variation autoencoder, which is totally different from autoencoder, and it had the very nice property that somehow address the bottleneck in the autoencoder network. So in the variation autoencoder, each hidden attribute is not a number, but it is a probability distribution. And by saying it is a probability distribution, then each hidden attribute can be represented by a mean and a standard deviation, right? Right. So if we have a vector, a number of attributes, then we have a mean vector and a standard deviation vector, right? So we can say that the Z here consists of 2 parts, the mean vector and the standard deviation vector, right? And then with the variation autoencoder, the encoder can encode the input image into, a vector of probability distribution. For example, from this specific input, we have the smile here. We actually this distribution, and this is the distribution for the skin tone, this is the distribution for the gender, and this is distribution for the hair color. And from that, I mean, vector of probability distribution, the decoder can decode and generate the output, which is expected to be, I mean, somehow closer to the input than the autoencoder network, right? Okay. So here we discuss a little bit into detail about the decoding in variational autoencoder. We know that the output of the encoder in VAE, a variational autoencoder, is a latent distribution, right? So how to generate the output from this latent distribution? We can do sampling, right? When decoding from the hidden state, we take a random sample from the distribution of X hidden attribute to generate the input vector for the decoder, right? So if we take the sample and we will have the, I mean, the input vector of the decoder, right? So that we can use, I mean, add the normal input data for the decoder, right? So this is first sample and this is the second sample, right? And from that we can, I mean, decode, and this is a first output and this is the second output, right? And we expect an accurate reconstruction from any sample from the latent state distribution. That means that, okay, it doesn't depend on the sample, right? Because we take a random sample, so we expect that, I mean, for every sample, I mean, the output should be the same, okay? Okay, so okay, this is optimization of variation autoencoder. It's somehow similar to the autoencoder we discussed before. So we have the encoder try to encode the input, and it actually computes the probability of having this, I mean, latent distribution given X, the input, right? And the decoder actually want to reconstruct the input so that it want to compute, I mean, the X, I mean, the probability of having X given the latent dimension dash, right? And the dash we are discussing here is not a vector of, I mean, specific number, but it is a vector of, I mean, distribution, right? And for X distribution, we can represent by the mean and the standard deviation, the mu and the sigma, right? Okay, so how do we, I mean, learn the mu and sigma here? We can use a loss function. Actually consists of two parts. One is the reconstruction loss, right? And another one is the deregulation term, right? So the reconstruction loss could be, I mean, any loss that make the output to be as close to the input. It could be mean square error, or it could be whatever loss that have the property, right? And the second part, the regularization term, is actually the loss that forks the distribution of the learn of the network, right? The learn distribution of the network. The P with this, I mean, parameter having that given X should be, I mean, close to the, this is a nature distribution of the data, the PZ, right? Okay, and this could be used, we for the regulation term here, we could use the KLD version, right? Because this is, I mean, the specific mechanism to measure the similarity of two distribution, right? So the KLD version could be used in this regulation term. Okay. Okay, so here's this here's the demonstrations about different loss in optimizing variational autoencoder. If we just use a reconstruction loss, right? Or if we just say that, okay, we just want the output to be similar to the input, then the learned, model will have a uneven distribution, and it is a model that cannot learn a smooth representation of the hidden state, right? This is the case when we use only reconstruction loss. If we only use KLD version loss, and then we will have the network that cannot learn the representation of the original data. So because in the loss we have no information saying that the output should be the same as the input, right? So the model can only memorize the input data. And this is okay when we combine the two parts of the loss, the reconstruction loss and the KLD version. And then we can see that, okay, the model can clearly learn the distribution of different labels in the data sets, right? Okay, so how do we implement the variational autoencoder in learning framework? Okay, so we have the assumption that the hidden state distribution is a Gaussian distribution. Then the output of the encoder, should be two vector, right? One vector describing the mean and another vector describing the variance or the standard deviation, right, of the hidden state distribution, right? But it's the Gaussian distribution, right? Gaussian. Then we can specify the mean and the variance, right? So okay, that was the output of the encoder, the mean vector and the variance vector. Okay, you can say it's a standard deviation vector, right? So the decoder will take the inputs, which are the random sample from the hidden state, the output of the encoder, and then the decoder will decode, right? So this is the way we do the forward pass, right? If we know the input, if we know the network weight, then we can do the forward path from the input to the output like this one, right? But if we want to train the variational autoencoder in an end-to-end fashion, to backpropagate the information, the error signal from the output to the input, right? So in this case, we have the problem because we have this kind of random sampling here, and this somehow we need to find a way to backpropagate. From this to from the from this layer to the encoder network, right? So the idea here is to use some mechanism called the reparameterization trick, right? So this trick is like this, right? We want to model the test here is this function, right? Probability function. So we can use a reparameterization trick to actually, convert this, approximation into a formulation like this, right? So we can approximate this by using a unit Gaussian, and then we shift the random sample by the latent distribution mean mu, and then we scale it by the latent distribution variance sigma, right? So this is the thing we want to model that after the this random this shift and scale, we would have that equal to mu plus sigma multiplied with the epsilon, let's say, right? And if we convert the dash to be this, then we can do normal backpropagation, right? Okay, it's now we have that is equal to a function of x and epsilon, right? Then we can backpropagate as the normal function, right? Okay. So this is an example of varying um, um, the value of a hidden variable in the encoder output. We know that x dimension of the z, the encoder output, meaning represent a meaningful hidden feature. For example, here we can see the example of changing a feature that represent the head pose, and we can say that we can train the pose face from left to right. Okay. So here is another example where we show the two hidden variable learned by the VIE network. For example, one could represent the smile distribution and another one could represent the head pole distribution. So we can try to vary the value of the head pole distribution and smile distribution and see the different output, right? So ideally, the hidden variable in the Leiden vector are completely independent of each other. So so that is to say that ideally the distribution in the hidden latent space should be independent, right? So we could force the model to learn independent distribution by adding a cross matching to force the hidden variable to be independent of each other, right? So this is such optimization that you can try if you implement the variational autoencoder, right? So in summarize, the variational autoencoder can allow us to train in unsupervised testing and to have the network that can encode the input into a smaller number of dimension hidden space, right? And it uses a reproductive objective function to actually construct the output to be similar to the input, right? And in order to train this variational autoencoder, we can use a reparameterization trick to enable end-to-end training. To allow the error signal to pass from the decoder into the encoder layer, right? We can interpret the hidden variable learned by the variational autoencoder by varying their value and observing the trending of the output, right? For example, we can vary the one specific hidden variable represent the head pose, and we can see the head moving from left to right, for example, right? We can use a VIE for generating new data, and the new data could be used for 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 training data of all the sample of all the tasks, right? Okay, so any question about VIE variational autoencoder model?
Could you please compare the conversion time of autoencoder and VIE?
Compare the what?
The conversion time.
Um,
It is slower in the VIE.
it's slower than VE. Um, I don't think so, right? So I haven't tried it yet, so I cannot say more concrete. But from my impression, I think that it doesn't mean it should be slower than autoencoder, right? Any other question?
I have a question.
Yes.
Okay, so in VIEs, how that we in the latent space we learn the mean and standard deviation of each attribute, right? So how do we know that which mean and which standard deviation belongs to which attribute?
Uh, okay, that's a very good question. What I showing here, what I show you here is that's the example saying that we can vary one attribute and that attribute actually corresponding to the head pose, right? So if you want to know which attribute represent what, then you can just you have to do the experiment, right? To vary the distribution to see which is a proper which is the attribute that belong to um, that hidden attribute, hidden variable. Maybe it's not smile, not helpful. It is something else. You have to do the experiment, right? Any other question? Okay, then maybe we can take a break um, before coming to the next part of the lesson. Okay, see you in 5 minutes. So let's continue our lesson to discuss the last topic on generative adversarial network, GAN, right? So generative adversarial network is a generative model containing two opposing networks. The generator network okay, so I think that I need to correct a little bit the slide here. Okay, so this is not a classifier but the discriminator, right? Okay, so sorry, discriminator. Okay. Okay, so GAN consists of two opposing neural networks, the generator and the discriminator. The generator network turns a noise vector into an imitation of the data, fake data, right, to fool the discriminator. And in its turn, slide. Okay. Em thấy slide chưa?
Tôi thấy rồi ạ.
Okay, rồi. Okay, so the discriminator try to distinguish between the real data and the imitation of the data, the fake data generated by the generator, right? So that means the two networks, the generator and discriminator, try doing the opposite things, right? One is trying to generate the fake data, and one is trying to distinguish the fake and the real data, right? Okay, so let's have some example to understand the GAN network, right? So first, let's discuss about the generator. The generator try to generate fake data from noise, right? Starting from a noise vector, right? It starts to generate some fake data, right? So in the beginning, the fake data could be, the point, right? Okay, and now it's the discriminator turn. So the discriminator will try to distinguish the fake and the real data. For example, this green dot here are real data, and this dot here are fake data, right? So the discriminator would try to maximize the probability for the real data and minimize the probability for the fake data, right? So for example, during the optimization of the discriminator, it will try to maximize the probability for the real data and minimize the probability for the fake data, right? Okay, and now the generator will try again, and now the generator will try to improve the quality of the generated fake data, right? So the generator knows that, okay, in the beginning, the real data is here, the fake data is here, right? And now the generator will try to minimize the gap between the fake and the real data, right? And now it improves to make the fake data close to the real data. And now, again, it's now the task of the discriminator to, identify the real and the fake one, right? And now it's again, okay, maximizing the probability for the real data and minimizing the probability for the fake data, right? Okay. And now come to the generator, right? It's again try to minimizing the gap between the fake data and the real data, right? Okay, and now it's getting close, right? And now it's the discriminator will again try to distinguish. It get a harder task to distinguish, right? So by training the discriminator and the generator in this way, then both the network can improve, I mean, in parallel, right? Whenever the data get improved in terms of making the fetch data to be close to the real data, then the discriminator will have a harder task of distinguish the hard and the fake and the real one. And then it can improve the discrimination model, right? Okay. Okay, so the loss for the GAN would be something similar to the Minimax game, right? And we train the GAN jointly via Minimax game. That means you can train, I mean, jointly the discriminator and the generator network. So for this loss, the discriminator want to maximize the objective, such as EX close to 1, and they mean the distribution for the real data close to 1, and the distribution for the fetch data close to 0, right? And in its turn, the generator want to minimize the objective so that it want the z close to 1. That means the distribution for the fetch data close to 1, close to the real one. Okay. Okay. This is a training GAN pseudo algorithm, right? You can use a normal minimax stochastic gradient descent for training generative adversarial network. The number of steps to apply to the discriminator is k, and this is hyperparameter. And for this algorithm, we use k equal to 1, the least expensive option, right? Okay, so let me go into the algorithm a little bit. So first we have a loop for number of training iteration do. For k step do, you sample minibatch of m noise sample from noisy prior, so this is noise better, let's say. And then you sample minibatch of m example from the data generating distribution p data. And then you update the discriminator by ascending its stochastic gradient, right? And then you enter for, and again you sample the millibatch of m noise sample from noise prior, and update the generator by descending its stochastic gradient. So here you update the discriminator, and here you update the generator, right? The discriminator will try to, I mean, maximizing the differentiation between the real and the fake one, and the generator will try to making the fake and the real close, right? And then you end the loop, right? The gradient by update can use any standard gradient by learning rule, and you can use momentum or ADA or whatever you want, right? Okay, so here's some example of GAN network. For example, you can use GAN for emit-to-emit transformation, right? For example, you can translate, I mean, the drawing here into a real object, right? And in this setting, you have a pair learning sample, right? Of the drawing and the associated painting object, right? And in other tasks, you can have unpaired image-to-image transformation. For example, you have this is an image and this is the target image with different, I mean, content, right? The image are totally different from each other, but you still want to learn the drawing style at the end, right? Okay. For example, here is a pick-to-pick application, and in this pick-to-pick, the author trained a conditional GAN, right? GAN with condition to map X photo, X drawing into the photo. So in this pic-to-pic setting, the discriminator D learn to classify between fake synthesized by the generator and the real. The real is a pair of X and the photo, right? And the generator Z learn to fool the discriminator. And unlike unconditional GAN, both the generator and discriminator observe the input X match, right? For example, in here, okay, so this is the X, the drawing. Okay, the generator will try to generate the photo, right? And then the discriminator will look at the photo and the drawing to say it is fact or real. Okay. Okay, so this is zero architecture of conditional GAN, right? Okay, so for example, here you have the this is the noise vector, and it is some information you put into the generator to generate the fake image, right? And for the discriminator, it takes the real image, the fake image, and some property, and then it can distinguish it, the input is fake or real, right? Okay. Okay, so this is cycle GAN. Cycle GAN is actually GAN to learn transformation across domain with unpaired data, right? It is important to say that we have unpaired data. So the idea here is to have, two model to first generate from the X image, try to preserve the photo in the Y setting, and then from that Y setting you generate back the photo into the X setting, right? So that in that scale you can transfer the image from one environment to another environment without the pairing data, right? Okay, so if you look into the internet, you can see a lot of impressive example of using GAN in reality. For example, here you can do generate a human face, and you see all of the red face here look really, natural for first, right? So it's really hard for the human to distinguish which one is real and which one face, right? Okay. Okay. This is type by generator. For example, you can add the glasses to the face. You can add the change the hairstyle, change the, skin tone, whatever, by using the GAN model, right? So for example, here, condition again. You can say, okay, I want the image to be a male with black hair and whatever, with sunglasses, and then the red image will have that property, right? Okay. Okay, so to summarize, in this lesson for today, we study a little bit of autoencoder, variational autoencoder, and the network learn lower dimension latent space and sample the latent space to generate input reconstruction. For generative adversarial network, we compete the generator and discriminator, and to make them, both improve during the training, right? Okay, so these are some references you can take a look at. In the share folder, I said to you on World Driver, you can also see some, material I put in the folder to be more clear on the topic for today. So do I have any question? Hello. Okay, so I suggest that you go to the D2L AI website again. Okay, let me copy to you the link. Okay. Okay, you can take a look into that chapter and to first read it and then open the notebook for it to do some practical exercise on the implementation of generative adversarial network. Okay, so as usual, I will leave you alone for maybe 20 minutes and then I will come back, right? Hope we will have some time to discuss on the work. Okay. Ok, cho chúng ta, mình thấy có một vài bạn thì nó có câu hỏi liên quan đến phần bảo vệ bài tập lớn. Dự báo trước thứ tự bảo vệ các nhóm về thuyết trình, hay mỗi nhóm chỉ cần cử một vài người đại diện thuyết trình thôi ạ? Về cái phần này nhá, thứ nhất là về thứ tự bảo vệ các nhóm thì mình nghĩ là thứ tự này thì do mọi người lựa chọn thôi. Nếu mà không có thay đổi gì thì mình có thể lấy cái chính là cái thứ tự chính là danh sách nhóm 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Mọi người có muốn thay đổi thì mọi người có thể là trên cái file Excel ấy thì mọi người có thể là chèn thêm một cái cột, tức là thứ bảo vệ vào đấy, và xong buổi hôm đấy thì chúng ta gọi theo thứ tự đó. Thì trong mỗi thư mục driver thì mọi người nhớ chia sẻ cho tôi là gì? Thứ nhất là cái file báo cáo này, thứ hai là cái file slide này, và thứ ba là các mã nguồn nếu có, mã nguồn và dữ liệu nếu có, đúng không? Về thuyết trình này thì mỗi nhóm chỉ cần cử một vài người đại diện hay thuyết trình. Về thuyết trình ấy thì mình nghĩ là có thể là chúng ta sẽ cử người đại diện về để trình bày. Đấy, như cơ bản là những người mà được trình bày thì tôi sẽ cố gắng là đánh giá điểm cao hơn cho các bạn được trình bày, tại vì cơ bản là các bạn có sự chuẩn bị, và thứ hai là mình cũng nghĩ rằng các bạn trình bày là các bạn mà có cái gọi là cái năng lực tốt trong nhóm. Nếu mà nhóm chúng ta mà bố trí được thì có thể là nhiều người trình bày, mỗi người trình bày một phần, nhưng mà tôi sẽ hy vọng rằng là sẽ có phần đặt câu hỏi. Phần đặt câu hỏi thì có thể các câu hỏi đến từ phía giáo viên và cũng câu hỏi đến từ phía là các cái nhóm khác. Thì trong quá trình bảo vệ ấy, thì mình sẽ cộng điểm cho các bạn mà các câu hỏi hay, góp ý hay dành cho các nhóm đã trình bày. Và tôi cũng hy vọng rằng là cố gắng là mỗi thành viên trong nhóm thì phải là tham gia vào trong cái việc trình bày đó. Rồi về thời lượng thì như tôi thấy ở đây là chúng ta có 10 nhóm, thì đâu đó là chúng ta sẽ có thể là có thời lượng lên tới là 30 phút cho một nhóm, tức là mỗi nhóm có khoảng tầm 15 phút để trình bày và sau đó là 15 phút là hỏi đáp. Thì chúng ta sẽ có trên là 12:30 đến thế là mỗi buổi chúng ta sẽ có thể là bảo vệ được mấy nhóm nha. Thế thì chắc là chúng ta số lượng thì mỗi buổi chúng ta cũng thể bảo vệ được đâu đó phải đến khoảng tầm 4 nhóm đấy. Thì chúng ta sẽ mất khoảng tầm là 2 buổi rưỡi. Nhưng mà cứ du di là chúng ta sẽ có khoảng tầm 3 buổi một nhóm đi. Đấy. 3 nhóm một buổi. Đấy. Nếu mà chúng ta dồn lại được thì ok, chúng ta sẽ có các buổi sau hơn để chúng ta có thể chia sẻ thảo luận về cái hướng phát triển trong cái môn học này. Và bọn em có góp ý gì cập nhật thêm về môn học, hay là tóm lại là mình nghĩ là có thể thêm thời gian về trao đổi về môn học. Không vấn đề gì cả. Rồi có ai có câu hỏi gì nữa không nhỉ? Alo. Thuyết trình bằng tiếng Anh hay tiếng Việt thì cái này mình nghĩ là sẽ mình không rõ là mọi người thích thế nào, mình nghĩ thôi cứ để mọi người tự chọn đi. Chúng ta có thể là chọn cái ngôn ngữ mà mình cảm thấy là phù hợp nhất để chúng ta có thể trình bày. Rồi có câu hỏi gì nữa không nhỉ? Còn câu hỏi nào nữa không nhỉ? Rồi về thứ tự bảo vệ thì đấy, các bạn có thể là sắp xếp lại trong lớp, đúng không? Còn nếu không thì tôi sẽ theo cái thứ tự danh sách 1, 2, 4, 5, 6 thôi. Chốt lại một lần nữa là mọi người nhớ là submit cho mình là cái thư mục driver trước 12 giờ đêm thứ 3 tuần sau. Sau thời điểm đó thì tôi sẽ download xuống, đúng không? Và tôi sẽ bảo vệ trên cái hiện trạng đấy thôi, đúng không? Mọi người check lại cái phần permission này, chia sẻ cho email là chungtva@soict.hoostmail.vn, đúng không? Để tôi có thể download được nhá. Nếu mà tôi không download được thì tôi sẽ coi như ở nhóm lục muộn. Đó. Rồi, thế còn về phần thực hành lấy về cái GAN model trên cái Deep Learning Tool AI ấy, đúng không? Thì cái đấy thì mọi người có vấn đề gì không? Anh chắc chúng ta cũng follow được thôi, đúng không ạ? Ok, vậy thì lớp chúng ta kết thúc tại đây nhá. Để hẹn gặp lại mọi người trong tuần tới. Rồi, chào tạm biệt mọi người.